This is simple linear regression, and we got one x and one y. And it's supposed to be a straight line that we can put through the points. So far we've used an x and a y, like length and weight. Right? It doesn't have to be just an x. X can be made up of other things, like if we're doing fish length and weight. They also measure the thickness and the height. So that if I have weight and I have length and width, then if I multiply them all together, I have a cubic, which is well related to weight. You can draw a fish in there, and it's a 3D fish. It's a smiling 3D fish. But if I have all three of those together, I can have weight is equal to an intercept plus a slope, and x is length times width times height. So that I still have one x and one y, and I have a better linear relation than before, but it's all same simple linear regression stuff. So I just have an x that's made up of more than one thing. Also, with y, sometimes if I get something that looks fan-shaped, which is not what I want, I've got x and I've got y, I can take the natural log or the base 10 log of y. You familiar with logarithms? What's the logarithm base 10 of 1? You can put it in Excel. The logarithm is 10, that's not 10, 10 to the a, where a is the number. So for 1, if a is 0, I get 10 to the 0. So this is the original number. I have 1. The log is 0. If I have 10, the log is 1. So the logarithm is that exponent. 10 to the 1 is 10. 10 to the 0 is 1/100. Base 10 log is 2. That's 10 squared. So I took a scale that goes from 1 to 100 and made it 0 to 2. So the logarithm literally squashes things. It just smashes them down. If I can get a line out of that, that's good. So if I take the logarithm of this fan shape, I just squeeze it so that it becomes less fan-shaped, and if I get it squeezed enough, it's linear and it's not fan-shaped. So I can change the x and the y to make a straight line. And that's all I'm doing. I'm going to make a straight line, and I don't care if it's justified or not. For example, for percentages, the suggested transformation, if this is a y, this is like the percent of people who do something. The suggested transformation is the arc sine of the square root of the percentage. I take the square root of the percentage and I take the inverse of the sine, and it makes a straight line out of percentages. There is no justification whatsoever for that except that it makes a straight line. This is one of the more ridiculous transformations that I ever saw. So anything we can do to get a straight line, 1x, 1y, is good. So look at, what do we need? Myopen math. And here is a tree and fish line transformations. It's in section 5. And this is tree height in feet and age in years. And I'm going to make a scatter plot of that. So mark them both. X is first, because that's the only way this one works when I'm doing it, blocking numbers off. And in this, I get a sigmoid shape. This is an S-shaped growth curve. This is common for little kids, children. You got a little brother or sister? They were real small, right? You got a brother in particular, younger than you. He was way down here, and you were up here. Then what happened?
He's taller than me now.
Yes, he's taller than you, because he went zoom. So he grew, and women grow the same way, except at a different rate. Start here as a little kid, then there's a growth spell, and then you start to top off. Right? So for women, the general trend is to be small, then you get larger, faster, and then you stop growing so much. Your little brother started here, same place, went further, slower, and then went like that. So that what used to be the little kid that you could boss around suddenly is much bigger than you. So this is a sigmoid growth curve. So fish, trees, almost anything that grows starts small, has a low period of growth as they're becoming established, and then they have a almost linear growth and then reach a top. This is like bacteria or Ebola infections. Ebola infection is bad. So they get a couple of Ebola patients. They want to stop it right here as soon as they can spot it, because if it starts to grow, it grows like that. So suddenly, you don't have 3 patients, you've got 20. Then you've got 80, you've got 500, and you can kill off the whole population. So any kind of epidemic, COVID-19, same deal. Starts here, a few people get it, then it goes linear in growth, and it goes up fast. So in all of these things, it isn't a straight line. But if I take the log of this, I get a much flatter line. And the only reason I'm doing it is so that I get a straight line. If I want to predict the growth of bacteria, Ebola, your little brother, I take a log and it literally squeezes it down. So instead of going from 1 to 10 to 100, suddenly it goes from 0, 1, and 2. Just flattens it. So there is no justification mathematically or biologically for doing that transformation. It just makes a straight line, or helps make a straight line. So if you look at this data, this fish and trend, it's got an obvious curve. And I don't want a curve. I want a straight line. Look at the fish. Make a scatter plot of the fish weight and length. We're going to predict weight from length. So length is the x, weight is the y. Put in a plot. What do we get? Fan shape. Why? When you were in the first grade, how different were the heights of the people around you? Yeah, pretty similar because they're all down here somewhere. Then as people age, they get taller or shorter. There is more opportunity for the spread. That's what's happening with these fish. As they go along, depending on the habitat that they're in, what stream they're in, what their genetics are, they have the potential to be very big or very small for their age, for their length, so that these guys have more warmer water, have more food, more whatever, ate more crawdads, crayfish, what do you call them? Crawdads. That's the. So this is not good. I don't want this. So I can make a transformation that will change these things. So look at this one. First, we're going to try to do the log transform. So I want to go to a spot next to height in feet, and we're going to take the natural log of the height. And you can use a base 10 log, you can use a base 2 log, whatever. Logarithm, the base really doesn't matter because you can transfer between them pretty easily. So this is equals ln. And it returns the natural logarithm of a number. Paren log of the height, and I get a bunch of decimals. There's got to be a way to control that. I need to look at that more. That really is messy. Now we want to plot the log of height versus the age in years. So I'm going to make a new plot, and I can't just mark them now because I got feet in between the age and the log of height. So I have to start from scratch. Also now, if I start here, I have to select data. I can right-click in this and get this menu that's got select data. Or if I just click in here, up at the top is chart design. And here is select data. This is exactly the same select data command as before. It's just in a different spot. So it's another way to find select data. And either way you do it, it's going to be exactly the same. So I'm going to select data, add a series, give it a name, I'm going to call this the log of height. By age. When you get a bunch of graphs, it's best to put names on these things. I usually don't put names in, and then I've got 8 graphs and I don't know what's what. So it's just a pain in the neck. This will label the graph. I want to select the x values. And these x values are age in years. Mark the x. Series y values, and I want to select the log of height. And I'm not quite sure because I've got my chart in the way. Did I get it? 35, 35, yeah. So I get this graph. And my 2 graphs, this is the log of height. Here is the regular height. This one doesn't look flatter because it's still on that kind of scale. Look at the 0 to 4.5 for the elevation, for the height of y. That fits between 0 here and 5 there. So if I put these on the same relative scale, instead of 0 to 4.5, I'm going to make it format axis 0 to 80, the way the other one is. Not 480, 80. Here's my original data, and this data, the transformed, is basically a straight line now on the same scale. I just flattened it, and I have no justification except I want it flat. I want a straight line. So by changing the variable y, I can make a better straight line and run a regression on it. Look at the fish. Do the same log transformation for weight. So in this column, I'm going to have ln, and logarithms in Excel, you can say ln and get a natural log, log, get a base 10 log, or loga, I think it is, and it will give you whatever you want for the log. This is going to be natural log of weight. So if I go in here, and instead of ln, I do log, here's my choices. I have a log 10, I have a log e, or log returns the logarithm of a number, the base you specify. I can do log 2 if I want. But I'm just going to do ln because it's easier. And I got weight. Copy that down. And I want now the scatter plot for the log of weight versus the length. So I'm going to insert, and I just need a blank chart. Right-click this time to select data and add the series. Excuse me, I left my plot on top of my numbers. Add, this is ln of weight by length. And the name doesn't matter in the least. You can call it a name or not. Select range for x, that's going to be the length. Select range for y, that's going to be the log of y. And there is my graph of the log of y weight. Come on. So I went from a fan shape. I've still got a fan shape, but it's much narrower. It's just flattened. Just by changing the y, making the log of y, I got a different setup. Go back to the log of height by age. We're going to put a log or a straight line in here, a linear regression line. And I'm going to use trend line. Log of height by age. Right click on there, on one of the points, and add trend line. We want a linear trend line. We want to display the equation on the chart and display the r squared on the chart. So there is the line now, and it's a line because I just squeezed the crap out of it. I removed all kinds of white space in there, and I have a regression line that predicts the log of the height. So now my equation is y is equal to 0.0363 times the age plus 2.5. And if I use that equation, I will get a prediction of the log of height. So if I want to predict the log of height, according to this equation, then I'll put it here because I can see it, equals, the slope is 0.0363 times the age plus the intercept, 2.51. No need to get carried away. And I'm going to copy that up and down. The only reason I did it in that spot was because I wanted to be able to see the graph so I could get the slope and the intercept. So there's my prediction. It does not predict y directly. If I want to predict y, the actual height, I have to take e to the power that I've got for the prediction. So everything for the graph, for the regression, now predicts the log of height, not height. So I gave up something. To get a straight line, I added a step to it. and I've made the minimum sum of squares of residuals for the log of height, not height. I got a straight line, but I have to do more to make it work. I have to put height prediction, if I want to put it here, it's got to be exp, because it's a base e log of that. And there's my predicted height. I did log, I predicted log, then I got to do e to that power to get it back to actual height. Pick a spot down here, pick a blank spot. This is going to be radius. And we can just put in numbers. 1, 2, 2, 1, 2, and I'm just going to go down here and put in a series, fill, series step 1. All I want is numbers 1 through whatever. And I happen to get 1 through 13. It doesn't matter. What's the area of a circle with that radius? Equals 3.14 times the radius squared. And copy that down. So I have a perfect relation between radius of a circle and area of a circle. I'm going to make a scatter plot of those two things. Just mark them. I want radius as x. Insert the chart. And I get just exactly what I expect. I get a curve. The relation is perfect. I still get a curve. So I need, if I want to predict area from radius, what am I going to use instead of radius? What makes it a perfect straight line? I'm going to square the radius. So here equals 1 raised to the 2, and I get 1. And I come down here, I get the rest of them. 1, 4, 9, so on. I'm going to put in a new plot, insert, and I'm going to plot area versus radius squared. My x now isn't radius, it's radius squared. Select data. The x values now are radius squared, and the y values are area. What am I going to get now? A straight line, an absolutely straight line. If I did the regression for this, what's the slope going to be? Right-click on one of those. We'll do the trend line and put the equation and r squared on the chart. What's the slope? What was the formula we used to get area? Pi r squared. I used 3.14. That's what I get for the slope. I took a curve, and instead of using radius as x, I used radius squared. So I can change the y or the x, or I can change them both. Go back up to the tree height. And I'm going to slick these off because I don't need them at the moment. And I don't want the graphs anymore. A common transformation to predict tree height from age is to take the log of height and the reciprocal of age. I want a new column, which is 1 divided by age. This is going to be y, and this one is going to be x. So I still have y equals mx plus b. I got a straight line. But now y is the log of height, and x is 1 over the age. So it's equals 1 divided by age. So now, instead of using age, I'm using 1 over age. Copy that down. And I'm going to make a scatter plot now with y and x. But y is the log of height, x is 1 over age. Insert chart. Chart design, select data, add. The y range is log of height. The x range is 1 over age. There's 1 over age. That's x. And y is the log of height. I completely changed the look of the thing. I went from regular height and age, which had a sigmoid growth curve, to the log of height by 1 over age, and I get a straight line with a negative slope. The only reason to do this is to get a straight line. So I can use simple linear regression. I can do add trend line. There's the line, display equation on chart in the R-square. And there's my regression to predict height from age, except now I have the log of height from the reciprocal of age. And look at the R-square. It's almost perfect. So I took a sigmoid curve and made a ridiculous transformation for y and x and got what I wanted, a straight line. So now I pick an age, I multiply the reciprocal by minus 27.7, add 4.7, and I get the log of height. Then I have to change that log of height back into height. Right, so when I make a transformation, whatever y is the variable for which they are getting the minimized residual sum of squares, the least squares solution. So I'm not predicting height anymore. Height is second hand. I'm predicting the log of height. That's the price I paid to get a straight line. So I'm not using the original data directly. Right, so there's all kinds of transformations that are possible. Anything that makes a straight line is good. There's no justification for it. Like this one, I went from log of or height and age in years to the log of height and the reciprocal of age just to get a straight line. No biological or mathematical justification at all. I want a straight line, I got a straight line. Simple linear regression isn't necessarily simple. All simple linear regression means is one x and one y and a linear relation. And however I get that is good.